So, good morning all. Next we will see the topic energy stored in electric field. Now you consider a charge free space. That means a space which is free of charge. Now into that charge you have to move three charges Q1, Q2, Q3 from infinity. Okay, that is written here. Consider a charge free space. 3-point charge Q1, Q2, Q3 is to be moved into this space from infinity. Now let Q1 be the first charge to be moved from infinity. Infinity in the sense from a long distance. Okay. Now since a region is charge free, no work is to be done. That means right now that region is free of charge, and to that region you are moving a charge Q1. In this case there is no work to be done since this region is free of charge. Okay. Next what we are going to do is we are moving Q2. Q2 is the next charge to be moved into this region. Now in this case the region is not free of charge because this region now contains charge Q1, right, which we moved before Q2. Now since a region has a charge Q1 in it, work is to be done in moving Q2 to that region. Now due to charge Q1 there is a potential difference and is denoted by V21, right? That means now that region consists of two charges, which are the Q1 and Q2, right? Now the second charge we are moving into this region is which one? Q2, and earlier there was Q1. Now this Q1 will enforce a potential difference on Q2, which is denoted by V21. Clear? So this is Q1 and this is Q2, and due to Q1 a potential difference is seen on Q2, which is marked as V21. Next, Q3 is to be moved from infinity to this region. Now this region has two charges, that is Q1 and Q2. Now the potential difference on this Q3 will be due to Q1 and Q2, right? Therefore the potential difference due to charge Q1 on Q3 is marked as V31, and the potential difference due to charge Q2 on Q3 is denoted as V32. Now this is the overall figure. Potential difference on Q2 due to Q1, it is marked as V21. Then the potential difference on Q3 due to Q1 is marked as V31, and potential difference due to due to Q2 on Q3 is marked as V32. Now the total work done to move the charges Q1, Q2, Q3 is WE is equal to 0. This term denotes the work when Q1 is moved to a free charge region. In that case no work has to be done, plus Q2 into V21, this Q2 into V21, and this is the work done when Q2 is moved into this region. So Q2 into the potential difference will give you the work, plus Q3 into V31 plus V32. So when Q3 is moved into the region, then Q3 will experience two potential difference, that is due to Q1 and Q2. The potential difference due to Q1 is V31 and potential difference due to Q2 is V32. So the total work done on moving the charge Q3 is Q3 into V31 plus V32, and when you add up you will get the total work done. WE is equal to 0 plus Q2 into V21 plus Q3 into V31 plus V32. Now repeat, the first term denotes the work done in moving Q1, this denotes the work done in moving Q2, and this denotes the work done in moving Q3. Okay. Now you assume that if the charges are taken in the reverse order, that means first you are moving Q3, then Q2, then Q1. So when you move Q3, initially there will be no charge in that region, so no work has to be done. So here it is 0. Then second you are moving Q2, so the work done in moving Q2 to that region where Q3 is present is Q2 into V23, where V23 is the potential difference experienced by Q2 due to Q3, right? And third, you are moving Q1 to that region. Now in that region you will be having Q3 and Q2, right? So V12 represents a potential difference on Q1 due to Q2, and V13 represents a potential difference on Q1 due to Q3. Okay. So now the total work done is sum of these three terms. Okay. Now if I am adding 1 plus 2, I will get WE is equal to half Q1 V1 plus Q2 V2 plus Q3 V3. Add and rearrange. Okay, so finally Q1 into V1 plus Q2 into V2 plus Q3 into V3. So in general you can write WE is equal to half sigma K equal to 1 to N Q1 QK VK. Okay. So while writing this expression, we will be taking only the first subscript of V. Here you can see Q2 into V21. So Q2 V2. We will not be considering 1 here. So Q2 V2. Here also you can see Q3. Along with Q3 you are having the first subscript is V3. Here also V3. So Q3 V3. Similarly for Q1, here you can see the first subscript of V is 1 here, 1 V1. So while generalizing the expression, we will write WE is equal to half into Q1 V1 plus Q2 V2 plus Q3 V3. So this expression you have to by heart. Okay. Next, we will see the expression for work done in moving three different charge density, which we studied earlier. We have three different charge density. It is very important, that is line charge density, rho L, surface charge density, and volume charge density. Okay. So work done in moving a line charge WE is equal to half integral rho L V dl. Rho L, you know, it is charge per unit length. Now the work done in moving a surface charge is WE is equal to half integral rho S Vs Vds, where rho S is equal to charge per unit area. And the work done in moving a volume charge is equal to half integral rho V V dV, where rho V is your volume charge density, charge per unit volume. Okay. Now we have Gauss law del dot D is equal to rho V. This is one form of Gauss law. Okay. So now what I am going to do is I am going to substitute this 6 in 5. Okay. So I can write WE is equal to half. In place of rho V I am writing del dot P. Okay. Del is your gradient, so del dot D will give the divergence. Okay. So del dot D, then this V as such V into dV. That is equation number 7. So next we have the vector identity V into del dot A is equal to del dot AV minus A dot del B. Okay. This vector identity you have to by heart. Okay. Now I am going to apply this identity in equation 7. Now here in place of A I have D. Okay, in place of B I have B. So now what I am going to do is WE is equal to half integral. You can write del dot D. Okay, del dot D. Then this V here, that is written here, del dot D into V. Then this dV. Clear? Minus the second term is here, place of A you will write D. Okay, D dot del this V, that is written here D dot del V, then this dV. So what I have done is I have applied this identity on this equation 7. So I can write, I have separated the term, that is equal to half integral del dot dV minus half into d into del V dV, that is equation 9. Now I am going to apply the divergence theorem. You know, surface integral of A ds is equal to volume integral del A dV. Now what I am going to do is I am going to apply this equation 10 to the first term of equation 9, just to the first term. Okay, so I can write what, that is equal to half into, in place of here A, what I have D, isn't it? I have D. So dV, sorry, in here I have dV in place of, here in place of A I have dV here, isn't it? dV. Just compare this term and this term, this one. So in place of A I have what, dV. So accordingly what I can write, that is equal to half into surface integral of dV ds. So point to be noted, I am applying equation 10 to the first right hand side term of equation 9. So the second term is kept as such, minus half into integral d dot del V dV. Now you know the expression V is equal to, potential difference is equal to 1 by 4 pi epsilon 0 Q by R. So as R increases, as distance increases, what happens to be V also tends to 0. So if the radius of a region is increasing, what do you mean by, what do you understand by its surface area? That means the surface area is also increasing. As R increases, what happens to its surface area? The surface area is also increases, right? So in short I can say, when surface area increases, the potential difference will approach 0. So here, since we are integrating the surface, this term can be made equal to 0. So WE is equal to 0 minus the second term is kept as such. So that is equal to minus half. D we have epsilon 0 E. I am substituting it. D is equal to epsilon 0 E del V dV. We have minus of del V is equal to E. So what I am going to do is, in place of del V I am going to substitute minus E. So I can write minus half integral epsilon 0 E into minus E dV, which finally gives you half integral epsilon 0 E square dV, which is the energy stored in this electric field. And that's all. This derivation is very important. You have to study. And thank you.